Friday we talked about two more types of nuclear reactions beyond the alpha decay, the beta decay, and the gamma decay. We talked about fission and fusion. Fission, if you remember, kind of like, almost like, in a sense, like mitosis in biology, for those of you who've taken biology class. Mitosis is the splitting up of a cell, right? Okay, in biology class, sometimes you call cellular mitosis, you call it cellular fission. Okay, have you guys ever heard that term in biology? Cellular fission, the splitting up of cells, the dividing of cells. Okay? Nuclear fission is the splitting up of a nucleus. It's where one heavy nucleus becomes two or more lighter nuclei. Now, there's also some neutrons involved as well. Okay, what do the neutrons do? What does the neutron on the left-hand side do? On the reactant side do? Well, it starts the reaction, right? It gets absorbed by the fissionable material, in this case uranium-235, for a very, very short period of time, becomes uranium-236, and then decays into any one of a number of combinations of elements, in this case, krypton-92, barium-141. Now, it produces some extra neutrons as well. Sometimes 3 neutrons on the right side, sometimes 4, sometimes 2, depending upon the reaction that takes place. Okay? Now, what's the benefit of these neutrons? They can potentially start more reactions. So you can get what we call a chain reaction. This chain reaction is when the products of one nucleus cause more reactions. Now, we get in each of these reactions about 200 mega electron volts of energy that's generated. That's not a ton of energy. It's a lot for one reaction, but it's not a ton of energy kind of in the grand scheme of things. But if you have a whole ton of these reactions taking place, then we're going to get a whole ton of energy that's generated, okay? And that's going to be enough to power things in a nuclear power plant or to blow up things in the case of a nuclear bomb, okay? So where does the energy come from? Where does this 200 mega electron volts of energy come from? Where is it liberated from? Why do we get, okay, when we simply break down uranium-235 into krypton and barium, why do we get this energy coming out of it? What happens? Yep. We lose mass. Good. And that lost mass is what we call the mass defect. Okay, the mass that's lost in this reaction. The difference in mass between the products and the reactants, or between the daughter nuclei and the parent nuclei. Okay, we lose a little bit of mass, and then by the equation E is equal to mc squared, we get some energy generated there. Okay, that energy being the 200 mega electron volts. Now, the other reaction we talked about on Friday was nuclear fusion. It is literally the fusing together of 2 lighter nuclei to form one heavier nucleus. We're still talking about light nuclei, even the one that's produced, but it's heavier than the ones that we started with. So we end up with, in this particular case, there's more examples again, but in this particular example, hydrogen-2 fusing with another hydrogen-2 to produce a helium-3. Now, we get a neutron produced there as well. Okay, that's not a huge deal, okay, because it doesn't really come into play here. We get some energy produced. But what's the problem with this one? What's the problem with making this one take place? Good. These guys repel each other as they come closer and closer together. Now, to fuse together, they've got to come ridiculously close together. So the force of repulsion gets ridiculously huge, right? Ridiculously large. We have to overcome that force of repulsion. And we're going to overcome that force of repulsion by pumping energy into it. Where does that energy usually come from? Heat, right? It's usually energy in the form of heat, although technically it doesn't have to be in the form of heat. It just has to be quite a bit of energy. Now, this can sustain itself in a chain reaction, just like the last one did, but not by the neutrons produced, but rather by the energy produced. So some of this energy, some of it, goes into causing more of these hydrogen nuclei to come together. So it becomes kind of self-sustaining by the energy it's generating, just like the last one, fission, did. It becomes self-sustaining by the neutrons it's generating. Is that good? What's not good? What's not good about the products of nuclear fission? Somebody asked this question. I think it was this class, wasn't it? What's not good about the products of nuclear fission, Patrick? Good. They're radioactive. I don't know about you guys, but just like every time I think of EMR and mention infrared radio waves and microwaves, I get that electromagnetic spectrum song in my head. Every time I mention the word radioactive, I get Imagine Dragons going through my head. I don't know about you guys, but okay. If you didn't now, then maybe you do now. Okay. What's not so bad about the products of this one? Paige? I'm sorry? They're not radioactive. The products of this aren't radioactive. So there's pros and cons to both of them, right? The one big thing about this is the products are not radioactive, helium-3. All right, let's define mass defect again. We'll define it in the way that we've already defined it, but we'll extend that to a second definition as well. The mass defect, we've already said, is the difference in mass between the reactants and products. Here I am using chemistry terms as well. Between, what should we really say? Between the parent and the daughter. When a nuclear reaction takes place, there will be a difference in mass. There will be mass that disappears from the left side to the right side. That difference in mass is what we call the mass defect. Now I'm going to give you a second definition for the mass defect. There are more. And in the end, it sounds a little bit different. It sounds quite a bit different than the first one. But in the end, they all essentially boil down to the same thing. In fact, the first definition that I'm giving you here, that I just gave you, actually stems from the second definition that I'm about to give you. This one's the really confusing one. If you think this is kind of weird, like, hey, wait a second, we lose mass in the process of having a nuclear reaction? Okay, wait till you hear this one. This is the difference in mass. And again, they completely agree with each other. The first one really stems from the second one. It's the difference in mass between the nucleus and the nucleons. Now, what's a nucleon? Protons and neutrons. So, what we're saying here is this, and this is really strange. What we're saying is that if you take a nucleus that has, let's say, 92 protons and 143 neutrons, that would be uranium-235. If you add up the mass of those 92 protons and the mass of those 143 neutrons, it will be different than the mass of the nucleus. So it's like saying, we got 30 people in this room. If each of us weigh 50 kilograms, okay, that's lighter than average. But let's say we each weigh 50 kilograms because easy to do the math here. 30 people, 50 kilograms. How many kilograms is that total? 1,500 kilograms, right? So if we weighed everybody together, the entire classroom, it should weigh 1,500 kilograms, but it doesn't. If we take the mass of what makes up the nucleus, it weighs different than the mass of the nucleus itself. The difference in mass between the nucleus and the nucleons, the protons and neutrons, is called the mass defect. And that's what causes the difference in mass between the parent and the daughter nuclei. Now, what does that matter? What does it lead to? It leads to this, the binding energy. Now, there's a number of definitions that we can give you for this as well that all agree with each other, okay, but that sound different. We'll give you one. Okay, we'll give you one because that's really what we, kind of the aspect of it that we need to deal with. The binding energy is going to be the energy that's released in a reaction. The binding energy is the energy that's released in a nuclear reaction. Now, how do we find out what that binding energy is? This is where you can give me an answer. How do we get the value of that binding energy? I think you guys know this. What is it? E equals mc squared. C is the speed of light, right? What's m? Mass defect, right? In this case, m would be the mass defect. And it would be measured in kilograms. Now, couple of things down here as far as the units go. For the most part, we don't have to worry too much about using these units, with the possible exception of this one, but I want you to recognize them, okay, and what they actually measure. U is what we call an atomic mass unit. You might have seen that in chemistry class before. Okay, 1 atomic mass unit. And its value, 1U, is equal to 1.66, I believe, times 10 to the minus 27 kilograms. So it's a unit of mass. Okay, it's a unit of mass. It's defined. We're not going to worry about the definition of it here. I'm not going to write that down. But it comes from the mass of a carbon-12 isotope. Okay, it's defined as exactly 1/12 of the mass of carbon-12. That make sense? If you have a carbon-12 nucleus, 1/12 of that mass is exactly 1 atomic mass unit. Okay? Now, mega EV, MeV per c squared, that should be a big V, by the way, and GeV per c squared, what do you think those measure? That's why I'm telling you about these right now, is because they don't measure energy. They measure mass. Okay, they measure mass. As soon as we see that EV, right, what do we think, Tristan? We think energy, right? Okay, that's the absolute typical answer that I get when I ask that question, Tristan. Okay, they measure energy. The reason I'm pointing them out is because I want you to recognize that they don't measure energy, they measure mass. They're kind of strange units. We don't see them very often in Physics 30 at all. Okay, but if you do, okay, then they measure mass. Now, where does that come from ultimately? Well, if you take Einstein's equation, E equals mc squared, rearrange it, what do you get? E over c squared. Okay, what's E? Energy over c squared. Electron volts over c squared. Make sense? Now, I'd be surprised if you ever have to deal with either of those last two units. In fact, there's a pretty good chance you'll never even have to deal with the first one. Okay, but the last two especially. If you do, you can find its value by taking mega electron volts, taking whatever number you have, and multiplying it by 10 to the 6, multiplying it by 10 to the minus 19, 1.6 times 10 to the minus 19 to get electron volts, and then dividing it by 3 times 10 to the 8 and squaring it. So you can figure out what it is in kilograms if you need to. But we're not going to spend a lot of time on that because I'd be surprised if you do. This one, we'll focus on a little bit more here. There's a table here, and this is in your textbook, but obviously anything that you needed from this table on your exam would be given to you. Probably not in a table like this. Okay, that's much too straightforward, giving it to you in a table like this. It's going to be a whole bunch of stuff, some kind of context about some kind of, nuclear reactor in a submarine or something, okay? Along with the information that you need, some buried somewhere in that page of information. Let's take a look. We're going to skip an example here and take a look at the example on page 819. Okay, we're going straight to the good one. Okay, first one is too easy for you guys. You guys are too smart for the first one that I had up on the board. So let's go straight to this one. Calculate the energy released by this fission reaction. The energy released by this fission reaction. Wow. Okay, that's quite a bit to ask here right from just an equation. You know what it reminds me of a little bit? Sometimes when I go to the photocopier, there's a chemistry quiz sitting on the photocopier because Mr. Real sometimes sends his stuff down from his computer and then doesn't pick it up right away. So I noticed the chemistry quiz sometimes, and it's been a long time since I've done chemistry, like a long time since I've done real chemistry. And sometimes I see the quiz, and you'll just be given a simple word reaction, and you'll be asked to solve for something crazy, and it's like, boy, how would you do that? Like I look at it sometimes and think, you're given almost nothing. You're given a reaction. How are you supposed to find out how many milligrams of this was whatever? This is kind of like that. But in the end, just like those chemistry problems on those chemistry quizzes, they're not that bad if you're familiar with how to do it. Okay? How are we going to do this? Well, first of all, let's ask ourselves, where does the energy come from? The energy that's released comes from what? the change in mass, the mass defect. The binding energy comes from the mass defect. So if it comes from the mass defect, let's first get the mass defect. In order to get the mass defect, we need to get the mass of the left side, and we need to get the mass of the right side. Okay, let's do that. That table that we were given a couple slides ago is what we're going to use to get the mass defect here. All right, from that table, we're going to get the mass of uranium-235. So all we're going to do here is literally look down here. Okay, uranium-235 right here. The mass you can see is 235.043930. Now, I'm not going to remember when I'm flipping back and forth what that number is. Okay, so Nick in the back is going to tell me what that number is. 235.043930. And those are measured in atomic mass units. Okay, the good news is, if you got this question on an exam, it would likely be given to you in kilograms, not atomic mass units. But we're gonna do as an example kind of the worst case scenario. Okay, you're given it in atomic mass units. If it's kilograms, it makes it a little bit easier. What's a neutron? What's the mass of a neutron there, Nick? From the same table. Yeah, 1.665 atomic mass units. Okay, thank you. Now, that's the mass of each of the parent nuclei, each of the reactants, if you want to call it that. Let's look at the products here. What's on the right-hand side? We need barium-141, Nick. 140. 0.914412 atomic mass units again. Krypton 92. 926. 156 atomic mass units. And the neutrons, of course, is 3 times 1.008665 atomic mass units. All right, that's easy enough, right? That step, all we did is looked at our table, saw what the mass of each of these was, wrote it down. Now what I'd like you to do, guys, is these 3 rows over here, 1, 2, and 3, calculate the total mass of the left side. Rows 4, 5, and 6, please calculate the total mass of the right-hand side. Pay attention to the fact that that's 3 neutrons, right? Not 1 of them. What do you got there, Tanner? This is 236.052595. Thank you. Okay, that's the mass of the left-hand side. Now, this side of the room has calculated the mass of the green side, the right-hand side, right? So they know the answer to the question I'm about to ask right now because they can see the number right in front of them. Okay, this side doesn't because you guys have only seen the first side, the reactant side. What would you predict, this side of the room here, about this mass? What would you predict about the green mass over here, the right-hand side, Travis? Nope. It's going to be smaller. It's going to be smaller. We have what we call this mass defect, this missing mass. Now, it's probably not going to be very much smaller because we're not going to destroy most of this. It's going to be very little, but it should be a little bit smaller. What do you guys get? $235.866563, and that's right in line with what we predicted here, right? It's a little bit smaller, but not a lot smaller. All right. Now what are we going to do? Let's get the mass defect by subtracting them. Thank you. Okay, I'll get that in just 1 second, Tanner. Thank you. Okay, what do you get, Tanner, then again? 186,032 atomic mass units. Okay, that's not how much mass we have, but how much mass we lost in this process. How much disappeared in the process. So far, so good? I don't think that's crazy hard so far, right? You guys might not have known exactly where to start with this when we saw this question up on the board at first. Okay, but it seems pretty logical, I think, so far. Now, what do you think you're going to do with that number, this mass defect number? Go ahead. Convert it to kilograms. Now, if it's on a test, as I said, odds are, I think, on an exam, it would already be given to you in kilograms. Okay, that's the good news. But if it's not, okay, just do what we're about to do now. If it's already given to you in kilograms, then skip this next step. Okay, we want to convert this to kilograms. So let's use the same general method as we use in converting electron volts. Instead of saying 1 electron volt equals 1.6 times 10 to the minus 19, we're going to say 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. That means that 0.18032 atomic mass units is equal to X kilograms. 3.088 1312. Thank you. It's 10 to the minus 28 kilograms. All right. So what's that number that we've just found correspond to? What's it mean? That's our mass defect in kilograms, which is what we wanted it, right? All right. So how are we going to get the energy that's released now? Go ahead. Good. Multiply it by the speed of light squared. So let's say E is equal to mc squared. The binding energy is 3.0881312 times 10 to the minus 28 kilograms. And you really do want to be in kilograms here. Multiply by 3 times 10 to the 8. And we square that. What do we get? 10 to the minus 11. And that's going to be in joules, right? Is that okay? I mean, it looks like quite a bit of work here, but really, when you kind of take a step back from it, it's like, okay, all we got to do is add some numbers together, then subtract a couple numbers, and then multiply it by c squared. Or maybe do a conversion in there from atomic mass units to kilograms. Honestly, I've seen a question like this on an exam maybe a handful of times, probably less than 5 times. Okay. So I think the odds of you seeing it aren't huge, but they're certainly not 0 either. They're certainly, decent odds, maybe 1 in 4 chance. Okay. But really, like I say, I don't think it's a hard question. Okay. Once we've seen it done. All right. The questions I'd like you to work on for homework, and we're not going to work on these right now in class, but we will take a look at them tomorrow. And if we have a chance at the end of class, we'll let you work on them here. Page 819. Question number 1, exactly the same, right? Question number 1, exactly the same as what we've done, except you can see it's a different reaction. Hey, is it fission or fusion, though? Because this whole process works with fusion reactions as well, not just fission, right? Is this fission or fusion? Fission. Oh, it looks like it's the same one, right? Neutron plus uranium-235 goes to, oh wait, it's not krypton and barium, right? 2 different nuclei. So we're going to get a different amount of energy produced, okay? In order to balance out the neutrons, the mass number, we still have to have 3 neutrons. Sometimes it's 2, sometimes it's 4. In this case, it has to be 3. In the second question, this is a little bit different. Here we essentially have to balance the equation. How many neutrons do we need to produce in order to balance the equation? And then once we get that, we do the same thing as we did in question number 1. Tanner? I don't believe so. No, I don't believe so. Tristan?
How much error would you get
That's a good question. You would get, I don't know how much error you would get, but it would be wrong. Okay, the question, it's a good question, a really good question, actually. The question from Tristan was, how much error would you get if you use the masses from the periodic table instead of off the chart? What's the fatal flaw in using the masses from your periodic table versus what's given to us in the chart? Right, it's an average value. So it's pretty critical when we're dealing with uranium-235 here that we use the exact mass of uranium-235 and not some average mass of uranium-235 and 237 and 238 and 239 and whatever, right? Okay. An average is, I mean, we know it's going to be somewhere around 235. So if we're going to use an average, we might as well just make up a number, right? We need the exact mass of the exact nucleus that we're using. So bottom line is, don't use that atomic mass off your periodic table. Honestly, I don't even know why it's there for you guys in Physics 30. The only thing you're going to need off your periodic table is the symbol for the element, sometimes, to identify it in a question, and the atomic number. Okay. There's a good chance, in fact, on your diploma exam that you will not look at your periodic table a single time. There's a good chance of that. If you do, you're not going to get very much off it, atomic number or symbol. Okay, a couple multiple choice, but we're going to skip over those right now just because I want to get a certain amount covered today.